And I would like to invite Christopher to join me on the stage. Again, he's from Air Force Research Labs, and he'll be telling us about liquid metallings for printed stretchable electronics. So good luck to you.
Thank you, Kasia. Thank you so much for the invitation. I'm really happy to be here in Berlin. I gave a talk a couple of years ago, I think, at TechBlick virtually. This is so much better to be in person. So my name is Chris Tabor. I've been at the Air Force Research Lab in the US for about 15 years now. And in that role, the labs serve a very important function to try to risk-reduce technology. We really sit at the interface between academic research that's very fundamental in nature oftentimes, and trying to get technology that's transitioned out to our commercial partners. The labs do not make anything for the Air Force. We do that risk reduction of technology like I just mentioned, and try to explore new space that then can come down the road 3, 5, 10, sometimes 20 years out. And so this allows us to operate and collaborate with a lot of groups. And so that includes a lot of academic groups in the US, but a lot of international partnerships too. And so we have an arm here in London that supports a lot of basic research. So if anything up here is interesting and you think there's some collaborations, we very much like to function as a go-between between the fundamental science and trying to look for technology applications for that. So I'm going to give a story here. Where's this one? Okay. I'm going to give a story here of how we've done that with one material set specifically that's been very, very close to my heart over the last decade, and that's gallium-based liquid metals. So gallium-based liquid metals, I think these have come of age and been allowed, showed a lot in a variety of different platforms. When I first started this about a decade ago, these kind of were a little bit a niche area. Only a couple of people were working. Now there's a lot of groups working in this space, and so it's been very nice to see the maturation and the growth of these materials. But very, very briefly, the material set itself is a gallium-based alloy with some indium, about 25% indium. This creates a liquid at room temperature. It melts at about 15 degrees Celsius. And so this liquid has a very low viscosity. It behaves very much like water, but very, very high surface tension. And so this allows you to do a lot of things that you would do with liquid electronics. There's a very unique feature to this, though. And so I'm a chemist by training. I'm not an electrical engineer, so I'm using this for electronics. But I'm not an electrical engineer, and I'm not a metallurgist. But from a chemistry perspective, this is what grabbed my attention immediately, is that the surface will oxidize like many other metals do. And there's a variety of different metals that will have a very thin oxide layer. But unlike copper or silver, when you have this very thin oxide patina and you have an underlying metal core, in this case, you have a very thin oxide solid, and then underneath that, you have a liquid core. And so this creates a structure to the liquid that doesn't exist with most liquids. And so it really makes it a very interesting material set to study from a fundamental perspective, and really opens up at least what we thought, and I think we're beginning to see the fruit of this, a lot of application spaces that can utilize these properties. What I'm showing here is just a demonstration of that, where we've spread liquid metal across the surface, and it's hold this very thin layer down as it adheres to the surface, and that oxide forms and locks it in place. And then all the lettering is where we've removed that oxide. And so you can see the liquid metal as it pulls back away from that surface. The surface tension of the liquid draws it away from those areas where we've removed that oxide. And then you can see kind of the potential of being able to really control the liquid if you can control that surface. And so that's really what grabbed our attention and set us off on this path. And so when you think about, from this community, printed electronics, it's a liquid, so we can go ahead and extrude it out. That was the first thing that a lot of us went to early on. So this is some early work with Professor Michael Dickey, who got me interested in this space, being able to print this down on a variety of surfaces. Some surfaces it prints on very well. Some surfaces it doesn't, and you have to apply a voltage to be able to draw it out. These images at the bottom are just demonstrating being able to pull a voltage between the tip and the substrate, and using that conductive material property of the liquid itself to draw it out of the syringe directly where you want to be able to put it. However, this is a very serial process, and what we wanted to do is get to a parallelized process. Can we go to a more traditional printed, from screen printing, inkjet printing, that use colloidal solutions oftentimes to make very roll-to-roll large amounts of material at a time. So how can we move from that to a colloidal suspension is what we were really looking for.